Hi everyone, my name is still Mathieu, and this presentation does not have an experiment in the title because this is something I believe should be continued a lot. So today we're going to talk about generating rewrite patterns in MLIR. So MLIR, again, has this promise of shared abstraction. You have a domain that you want to write a compiler in, and usually you have one dialect for that domain. And then you can define optimization for that domain once, and you can reuse on any single of your pipeline that use that domain. So why is there so many arithmetic dialects in MLIR circuit and the entire MLIR ecosystem? So I'm cheating a bit because I'm including all the ones that I use to translate to something else like LLVM or WebAssembly. But if we remove those, we still have like 7 or 8 dialects that actually have vaguely the same thing, which is arithmetic, but still have wide differences and large differences that make them not the same. So why do we need so many of them? So if we take kind of like this 8 or 9 selection of dialects, some of them have Poisson semantics, which is something that was introduced by LLVM to essentially say that a division by, let's say, an overflow could be anything and you might want to optimize for this. Some of them have what's called 4-value logic or like even 9-value logic, which is something that's relevant in hardware. Some of them have undefined behavior for division. Some of them have value that are defined for the division. Some of them can have overflow. Some of them cannot essentially overflow by design. And for some of them, it's cheap to add a bit to the bit width of an integer. Let's say in hardware, if you have a 64-bit or a 65-bit integer for your compiler, it's kind of the same, where in LLVM, if you have 65 or 64 bits, that can be essentially a 2x slowdown. So these dialects are very, very different from each other, despite all talking about arithmetic. And this means that they have also very different optimizations. Almost all of them have associativity, not the case for arith because it might have the NSW flag, which makes this incorrect. Some of them can change, most of them can change multiplication by a power 2 into a shift. The problem in index is because we don't know the bit width, this might be illegal because this is Poisson if the shift is greater than the bit width. Some of them, because they essentially don't have overflows, if you multiply by a value and divide by it, it's equal to the original kind of value you had in the first place. But it's not the case for everyone because some of them have overflow and then everything breaks. So these dialects have very big differences in semantics, and that means they have big differences in the optimizations they have. So that's a bit of a problem because that means that if we want to have, let's say, something like ints combine in any of these dialects, we need to re-implement it again. And it's very easy to get things wrong because those like operation have very, very hard corner cases to get right. And there's a lot of optimization to write. There's a lot of operation in this dialect, and there's a lot of these dialects. And once you write optimization for your domain, you don't know if you kind of missed one or not. You don't know really which one are going to be the one that people are actually going to use. So the vision kind of I want to present is, what if we could synthesize, kind of automatically generate an ints combine equivalent for each of these dialects? What if instead of using a lot of manpower for this, we use a lot of compute power? And for that, I'm dissecting it in 2 different tools, which is, could we synthesize a base set of optimizations and lowering, with some guarantees of completeness? Let's say you only have all the optimization that has at most 2 operations in the left-hand side and 3 operations on the right-hand side. And once we have this kind of base set of optimization, we would let people use super optimization to kind of discover additional rewrites that are useful for their particular use case that do not fit into this kind of base set of optimizations and lowerings. So there's 3 tools I want to present, 3 tools we built and that we kind of trying to improve right now and trying to evaluate a bit better. One of them is kind of a rewrite synthesizer. You take a description of your dialect, which is something I'm going to go about it a bit later, and then for free, you get a lot of PDL rewrites. And those PDL rewrites have some limitation. You need to kind of set a maximum size in terms of number of operation on the left-hand side or the right-hand side. Otherwise, it's just like an infinite amount of rewrites you can get. And you can get kind of all of them. You have guarantee you have all the rewrites up to a certain size that also contains either a finite set of constant, let's say only 0 and 1, or that contains no constant at all. The second tool is a lowering synthesizer. You give an op, you give a dialect you want to lower it to, and then a tool is going to generate it. So this is something I generated this morning, actually. It's like a shift right in SMT gets lowered into then a shift right, a signed shift right in arith. But first, you need to actually take the minimum on the actual shift operand, because otherwise you're going to have poison in arithmetic, which is not the case in the SMT. In SMT, you want to have only the signed bits replicated all over. So this is kind of the kind of reason why you can have bugs in those kind of lowering, and that also the kind of reason that it's still kind of simple. So you still want to generate them. You don't necessarily want to use all the brain power to generate these things. And the third tool is a super optimizer. It's kind of something like super in some sense. You give an input program, you give here a description of your dialect you want as output, because here it's the kind of the same one you're using as your operation, and then it gives you a rewrite that's kind of applied in that program. So here just a multiplication by 2 can be rewritten into a shift by 1. And of course, this is just like on a simple example. The goal is to have this, like if you have a large program, it's going to give you, again, a large set of like these kind of PDL patterns of all the rewrites that can be applied into that program. So for that, we use what's called enumerative synthesis. So enumerative synthesis is something like it's pretty kind of simple to understand. You have a specification, let's say 2 times x. You enumerate all programs up to a certain size, and then you try all of them to see, is it the same? And by is it the same here is that, do they have the same behavior? Are they semantically equivalent? And for that, you really need like 3 different kind of components to make this work. You need an enumerator, which will enumerate all your MLIR program. You need a cost model to say, oh, I still want to only check the one that are actually faster than my original one. And you need an equivalence checker, something that can check, are those 2 programs equivalent? So let's look first on the equivalence checker. So this is something I presented with UU, I think it was 2 years ago, where essentially we use an SMT dialect to represent that. So let's say we have 2 programs as input. We use a compilation pass essentially to SMT. And then we just add some glue code, and we can pass this to like Z3 or an SMT solver. And it's just going to tell us, yes, it's equivalent. Or it's going to tell us, no, those programs are different because of like this input, they have a different result. So that's just for the checker. And now for the enumerator, the way we built it is that we wanted to have an enumerator of arbitrary MLIR program. You just say, oh, I want to enumerate all arithmetic program or all index program. But you don't want to rewrite something for every single dialect. You want something that's kind of generic. So for that, we use what's called the guided tree search library, which essentially tells us that if you want to enumerate all programs or all things, you just give a way of generating one of them. And each decision you're taking, you're just using kind of the tool to do this. So here, if we want to generate just like 2 values between 0 and 1, we're going to use the chooser.choose that's just going to tell us, give me a value. And you just put that in a loop. And the tool is going to take care of essentially looking at every single possible path you can have. First, you generate 0, then 0, then 0, then 1, 1, 0, 1, 1, etc. And it's going to give us like an enumeration. So this is how you can generate programs, or you can enumerate all of things by just saying a way how to generate one thing. For MLIR, the way we do this is, so then just generating one thing is like you choose an op of a given result type, then you choose the number of operands, then you choose the type for each operands, and then you just recurse it until you have the number of operations you want. So if you use this with the tool I just presented right before, you can enumerate all MLIR programs of a particular size. Of course, the problem is, how do you choose an op with the correct result type? How do you choose the right number of operands such that all of these programs are going to verify? Because you don't want to enumerate, let's say, an arith.add with 3 operands. It doesn't make sense. So for that, we actually use the IDL dialect to essentially get the information on how many operands is there in that program, what's the type of these operands in this result, do they have to be the same, and also, what's the kind of type of all of these. And this essentially kind of guides the enumerator, so then you can use it for essentially any kind of dialect. It just works out of the box. So then with that, we can do the enumerative synthesis. And that actually works for like the kind of second tool I showed you. If you want to do optimization, you just take an input program and you ask it to find an equivalent program using this enumerative synthesis. For lowering, you take an input program and you find what's called a refined program, which is essentially, if you have poison, you can compile it to anything else, but if you have something, you cannot compile to poison. And this very simple tool that gives us kind of a super optimizer, and that the example I showed you on the lowering, that's how it worked. So the problem is, I promised you that we could generate all rewrites up to a certain size. So do we just enumerate all left-hand side program, synthesize, and then for each of them synthesize a right-hand side program? The problem is there's a lot of these programs. If you look at 3 operations, there's like around 10 million programs, which means technically we'd have to check 100 trillion candidates to find essentially all rewrites up to 3 operations. But I'm claiming we can actually find all of these programs. So how do we do this? So the intuition is that in our enumerative synthesis loop, a lot of these candidates are actually redundant. There's no need to check for x plus 0 because we already checked for x, and those 2 programs are equivalent. Same for 0 plus x, and also 1 plus x is the same as x plus 1. So we can actually remove a lot of these cases, and that kind of drives a bit our algorithm. So the algorithm works as follows. We start by enumerating all programs of size 1. We find all the ones that are equivalent using what we call a classifier that I go into it. This will give us all the rewrites to that size, and will also give us 2 lists. A list for skippable, which is essentially patterns that are always wrong, that x plus 0. You never want to enumerate x plus 0 because you know x is always going to be better. Even in a subpattern, you always know you can replace that subpattern with x instead of x plus 0. And the second list it gives in the list of representatives. Note that it's not called canonical forms. It's essentially the one element per equivalence class. So for instance, when you have x and x plus 0, the element's going to be x. And those things are essentially the programs you want to enumerate. Those are the ones that kind of represent all programs that are equivalent. And then we pass it to a enumerator that's going to be a bit improved. And then we're going to do this for programs of size 2, then program of size 3. And this kind of iteration makes it actually feasible because we don't have to enumerate all these 100 trillion programs, 100 trillion pairs of programs. We can just essentially do it bit by bit. So first, let's go into the classifier. So to classify programs, so we have a list of programs. We want to find all the ones that are equivalent. We start with our enumerative programs, and then we put them into buckets. Essentially, we just evaluate them on random values. All the programs have the same random values. And then we check which one seems to be equivalent. So it's kind of an over-approximation on equivalence classes, programs that are equivalent. Once we have that, then we can use the kind of O event square algorithm, which is just check all pairs of programs in this bucket and find which one are equivalent. And this gives us the E classes, which is equivalence classes. So for instance, we have one that has 0 and 0 plus 0. We have one that has x, x plus 0, 0 plus x, and we have x plus 1, y plus x. So those are kind of sets of programs that are equivalent. We just call them like kind of behaviors. So it's like a set of we have C1, C2, and C3. We had 3 different behaviors. We select the first of these programs, decided by like the one that has the less number of operation, maybe the less number of constant, these kind of things. And those are kind of the representative sets I talked about earlier. So here, if you enumerated just 0, x, and x plus y, you kind of enumerated all behaviors that you show in this slide. Then we select all the others, and we say those are like the skippables. 0 plus 0 is never good because you can always enumerate 0. Same with x plus 0 and x. We remove the ones that are kind of redundant because 0 plus 0 is a sub-pattern of x plus 0. And then all the kind of relations between the skippables to the representatives is actually the rewrites we want. X plus 0 can be rewritten to x. Note that we don't have that for the x plus 1, y, and y plus x because they're just alpha renaming of each other's. It's just the same program. It's just the kind of argument that's switched. So once we have this, we can pass this kind of skippable and representative sets to the enumerator. So the enumerator will first have a generator, which is essentially just a way to enumerate all programs, but using kind of the known early behavior. So essentially, we choose just an op that has k operands, and for each of these k operands, take a representatives. Because the representatives essentially encompass all the behavior of the program of this size, we know we'll enumerate essentially all behavior of that size plus 1. And then we just unify the parameters. So essentially, we make sure that the kind of parameters / 3 variables on the left and the right are just going to be unified, and we have like multiple way of doing this. And then that's it. That's a better way of enumerating program that actually doesn't require us to enumerating the entire set of programs. And then we can remove the ones that we enumerated that are still bad, because sometimes the right-hand side, so here in the green, this X could be enumerated as 0, and we still enumerate again this X plus 0 pattern that we know is bad. So we take these patterns, these like skippable patterns, and for every program we enumerate, we just check if there's one of these skippable patterns. And if there is, we can remove that program before doing anything else. Because we know this program is never going to be good, because you can always replace this pattern with like just the subtree, which is the A plus B. And the problem is, we have many of these patterns. We have like 40,000 of these patterns that exist. So how do we actually make it fast? Well, we use the PDL dialect in MLIR. So PDL allows you to essentially take a large set of patterns, compile it into a very efficient automata. And the point of this is that the complexity of checking a pattern is actually linear in the maximum size of a pattern rather than taking the sum of the patterns. So that's actually a very, very efficient way of doing this. So that's kind of our algorithm. We had the classifier that finds the equivalence program, and then we have our enumerator that makes sure that for the next step, we only we kind of pre-select a nice set of programs to then use the classifier. So what can we kind of do with this? So we're trying to take the SMT dialect in MLIR, which has like this 30 operation. We also have true, false, constant, 0, and 1. And you're trying to see how many of these kind of rewrites exist in that dialect. So note that the rewrites we define are not always kind of optimizing rewrites. We might rewrite like, we might have rewrites that don't actually improve the runtime. Is just like essentially a way to always get one of the representatives from the set of programs we have. And then we just select the actual rewrites we want. So if we look at size 1, there's 6 programs in the size 0, there's 6 programs in the SMT dialect, which is true, false, 1, 0, the first argument, and then the second argument, I think, or there's one more. So we generate 100% of them, and it's taken a second. So okay, that's a bit slow. If you take the size 1, which is when you have one operation and constant, you have 372 programs. And now what we do is we still generate 100% of them, but there's only 20% that are representatives. That means that if you have a program of size 1, a random program of size 1 in the SMT dialect, there's 80% chance that you can actually rewrite it into one of the representative, and 20% chance that it is the representative. And from that, we also extract 115 skippable programs. And that means that on size 2, actually we generate only 16% of these programs, and after the skippables, we only enumerate 8.9% of these programs. Meaning that this small set of like 115 patterns means that we can already kind of discard a large amount of programs in size 2. From there, again, we find that only 4.5% of these programs are actually representative of the behaviors of the entire set. And we find 1,000 skippables. And all of this is done in like less than a minute. So we can find all kind of rewrites that can exist in these dialects in only half a minute. And then we do it for size 3 as well, which take a bit longer. This is done on my laptop, by the way. So it's like a MacBook M2 Air. And in 10 hours, we, instead of enumerating the 14 million programs that exist, we only actually had to take care of 1.8% of them, which means we drastically reduced the search space that we had to find all of these rewrites. And from there, we find again that only 1.3% of programs are actually important, or actually the ones you want in your programs. And we find like 43,000 kind of skippable patterns, which also represent 43,000 rewrites you would have in your IR. Again, we use this kind of skippable to kind of speed up super optimization / or lowering synthesis. And essentially, we kind of speed up our own super optimizer by like 3 or 5x by just essentially removing a lot of these like skippable patterns, because we know always one would be better. Note here that we don't need so for SMT, ARIF, and COM. And ARIF is much, much slower because its semantics are really annoying to deal with for SMT solvers. And that means it takes like almost an hour to do something that it takes a minute in SMT. And finally, we just kind of try to synthesize an SMT to arif lowering. There's like 34 patterns, so it's essentially 34 operations and plus the different types they can have. And in less than like a minute for each of these patterns, we can find lowering for like one operation. And in less than like between 2 and 10 minutes for each of these patterns, there's 2 of them that essentially has lowerings to 2 operations. Meaning that for the rest of the pattern, you need at least 3 operations in your like rewritten program to lower from SMT to arif. And I found like a case where you cannot do anything in 3 operations. You need 4 operations to lower unsigned division from SMT to arif. So that's something I'm kind of working on to see how much can we scale, can we go up to 4 operations. So in conclusion, we have kind of this tool to kind of generate rewrites lowering a bit. That takes a bit of time right now, but I think we can improve the runtime. I think that like simple people rewrites or lowering should not be manually written anymore because there's like so much work there is to do to implement something like ins_combine again. And it would be much better to have like this synthesis tool to make it work. So this is a first step towards that, and first step to like being able to do this in MLIR, which because it has been done in LLVM before, but not like at this scale for like MLIR. And there's still a lot of things we need to build, like a generalization algorithm. So then from a rewrite example, you can find a better one. And also like handling data flow analysis to then have like more powerful rewrites knowing that some data flow analysis has been built. So that's it. And thank you.
Thank you, Alex. Questions? So this is an interesting tool. I mean, have you thought about using a synthesizer for test code generation? Like you're like, oh, okay, I mean, we need more test programs to test everyone that talked about, right? I mean, so this could be a useful tool for such a thing.
So I've been using, so the first 2 parts, which is kind of the checker and the enumerator, to actually test a lot of the arif dialects in the test suite of MLIR. And I found, I think, 4 or 5 bugs at that point that I reported. So essentially enumerating all programs up to size 2, and then just seeing, is there any one of them that's like miscompiled? Yeah.
Interesting. Any more question? Okay. Let's thank Mathieu again. Thank you, everyone.